The periodic table of elements is a fantastic tool, but let's face it, there's a lot of information to unpack there. Fortunately for us, it was formulated to make quantum mechanical patterns easier to interpret and understand. By familiarizing ourselves with the rules and principles, we can go below the surface level and navigate the world of science with confidence. Protons in, electrons out. You've got this. All the elements on the table are listed in order by their atomic number, even if that means leaving huge gaps across the board. Seems suspicious, right? Though there are endless mysteries and adventures to be found utilizing the periodic table, we're focusing today on the atomic structure of electron orbitals and reviewing the four shapes of S, P, D, F, as well as their diagrams. We will also become more aware of the Aufbau Principle, Hund's rule, and the Pauli Exclusion Principle. First, let's talk about orbitals. What is that? It's the most likely place outside of the nucleus where an electron can be located. But remember, the electrons increase when the protons do. What does that mean for the orbitals? Do all of the added electrons fit on the ring outside of the nucleus? Well, the answer is no, they don't. Each orbital has a limit to the number of electrons it can hold. For example, the closest ring to the nucleus holds 2 electrons, so any elements with a higher atomic number than 2 need to expand beyond the first orbital, labeled n equals 1. In electron configuration, it's important to remember that 2 electrons fit per orbital. But let's talk about the Bohr model quickly, which has slightly different rules. For helium, with an atomic number of 2, the entire first orbital will be full. Notice it is on the highest row on the far right column. This is important for later. Neon has an atomic number of 10, so it will have 10 electrons. The first row holds 2 electrons, so the other 8 will have to move up to the row labeled n equals 2. The second orbital, according to the Bohr model, can hold 8 electrons, so this row is also full. This is in the second row and on the far right column. The third orbital, n equals 3, also holds 8 electrons, and the fourth orbital, n equals 4, holds 18. You'll notice if you continue down the right column that the orbitals will be full on each level. These are known as noble gases, and they are notoriously stable. Sometimes they are used as landmarks in electron configuration to create an easier recording. Well, that's all about the orbitals in the electron cloud and the last of the Bohr model for today. Let's get into the good stuff. Starting with the very top of the periodic table, let's look at hydrogen. Remember, this is row 1. Where is the placement of hydrogen? Well, it's on the polar opposite side of the table from where the noble gases are. In this section, the whole thing, including the alkali metals and the alkaline earth metals, is referred to as the S block. In a few steps, we can determine the configuration of hydrogen. So, H is in the first row. First row, start with a 1. H is in the S column zone. Add an S, so 1s. H is in the first column, not the second, so add an exponent per se of 1. So now we have 1s1. That's it. That's the electron configuration of hydrogen. Now how do we visualize that? 1 electron, 1 arrow. First row, first box. Unpaired electrons are an up-facing arrow. Now let's move on to helium and compare. He, helium, is in the first row. Start with a 1. Helium is in the S column zone. Add an S, so 1s. Helium is in the far column, but it only has 2 electrons. Despite being labeled as a noble gas, which it is, helium is 1s2. Picture it in that second column. Now let's visualize it in the box form again. What do we see? Well, the only difference between the hydrogen is now there's a second arrow in that 1s box. But what about ions? Ions are molecules and atoms like above, except they have a net charge. This comes from the gain, negative charge since electrons are negative, and loss, or positive charge, electrons. So the number of arrows would account for the change in electrons. If more electrons are added, like O2 negative, that adds 2 electrons. Then more arrows would be added to account for that. Remember, these aren't protons. They just usually tend to correlate with protons, when the element has a neutral charge, that is. So changing the configuration wouldn't change the identity. We're just trying to account for the charge. So for example, oxygen has 10 electrons instead of 8 with a 2 negative charge. This is an oxide ion. We would add the additional electrons to the raised subtext at the end of the last zone until the row is full and then move on. So the electron configuration for an oxide ion is 1s2, 2s2, 2p6 instead of the 2p4 in the 2p6 position. That's all. Just account for the change and add or subtract based on the positive or negative charge of the ion. The idea of the energy levels and their order remains important, as well as the idea that each area can only hold so many electrons. But what about the other zones? The zones are set based on their valence electron orbitals, or the outermost orbitals. Each column is full of elements with the same configuration of valence electrons. So the noble gases that are all mysteriously stable, the mystery is solved. They have a full valence shell, just like when our stomachs are full and we become significantly less unstable. We can use these noble gases to reduce the writing load, therefore reducing the possibility of mistakes by starting with the gas's atomic symbol at the end of the previous row and recording the rest of the electron configuration from that point. We'll see more of that later, don't worry about that yet. The Aufbau Principle symbolizes the relationship between protons and electrons. Increasing protons results in increased electrons present. We can use this relationship to determine where each element lies on the periodic table. Though we know already that the elements are arranged based on their atomic number, which is proton-based, we can also determine the position of elements based on what is happening with their electrons. This is known as electron configuration, and Aufbau Principle addresses it. Hund's rule addresses the boxes that have remained blank so far. How do we fill the boxes when there are more than one? Hund's rule implies that each box must have one arrow before any box can have two arrows. So for oxygen, which we've been looking at, the orbital diagram would look like the following, where we notice that the arrows fill up each of the 2p boxes before contributing an arrow to one of the pre-existing boxes. You must distribute first. Notice how there's a second arrow facing the opposite direction. This is an application of the Pauli Exclusion Principle, and it symbolizes an opposite directional spin, since only opposite spins can occupy an orbital. So for the 1s orbital, each of the two arrows must be facing opposite directions. Let's move on for now. The P zone is this whole category on the right with the halogens, noble gases, metalloids, and nonmetals. Since it begins in the second row, the initial row of elements is represented as a 2p. As with the S zone, the first column of the P category is 2p1 and so on until 2p6 at the end of the row. But this can't just be 2p1. All of the prior elements must be included in the electron configuration. So including 2p1, it would be 1s2, 2s2, 2p1. The transition metals fall into the D zone, but be careful, technically these begin in the fourth row. You'll notice this when you write the 4s zone for the corresponding D zone. But the top row of the transition metals is 3D. Counting down from the top of the table, the tippy top is 1s, the second plateau is 2p, the third place you can slide down to is 3d, and the fourth section on the bottom is 4f. SPDF 1, 2, 3, 4. Now the inner transition metals, the lanthanide and actinide series that are hiding on the bottom, represent the F block. These begin with the 4f orbital, though in reality sometimes there is a 5d electron instead due to the similarity of the energies. Note the placement of these series in their relationship to the 5d block. They're bound to have some overlaps. An example of the formatting through these blocks would be tungsten, which has an electron configuration of xenon, 6s2, 4f14, 5d4. There's that noble gas starting point. Told you you'd see it again later. Based on the placement of the inner transition metals, they must be passed through to map the transition metals into the D zone. So, in the sixth row, after passing through all 14 of the F elements, we can travel back into the D block to follow our remaining tracks to tungsten. Let's check out this diagram. It may seem a little funky at first, but let's look at it. What do you notice? I see that all of the lines have arrows traveling in the same direction. Okay, so starting from the top, like one does, it seems the order is 1s, 2s, 2p, 3s, and so on. It seems to be the same order as the electron configuration examples we looked at. The Aufbau principle comes full circle in this diagram, where the lowest orbital is filled first and the order of the orbitals is portrayed by the rays. So now we've seen the S, P, D, and F, superpowers don't fail, in orbital filling diagrams and electron configuration. So let's take it one step further and visualize how these orbitals may work within the atom. The unique energy of electrons and their position works with spherical symmetry to create a recognizable shape. So nodes, in between areas of high electron probability, are predicted to be low electron probability areas. Looking for electrons? Don't look in the nodes. So the s orbital is a sphere. The p orbital, it's not spherical, but it contains a node at the nucleus and two oblong shapes on each side, referred to as lobes. There are 3 orbitals, as we saw in the orbital box diagram examples earlier. The d orbital is similar to the p orbital, with 2 additional lobes to equate to 4 positioned lobes centered around the nucleus. There is a 5th orbital present here as well, though. The f orbitals are the most complex shapes. They contain 6 seemingly symmetrical positioned lobes centered around the nucleus. But there are 7 orbitals. Why are these orbitals different shapes? Well, these drawings are somewhat symmetrical in 2D. In all reality, there will be a third or z-axis present to make these 3-dimensional. The s orbital is symmetrical, which implies that electrons can be found equally in all directions from the center. The odds of finding an electron are consistent no matter where you look. There are no nodes or rogue lobes to mess around with electron distribution. The p orbital is often described like a dumbbell, and the d orbital is described like a 4-leaf clover. Pleasant, right? They're usually sorted into a variety of groups based on their tendencies, size, or geometry. Smaller orbitals usually mean that an electron can be more easily located closer to the nucleus. So, a smaller orbital will have more concentrated energy all over, and therefore the likelihood of finding electrons during location increases. But the electrons increase as the orbitals increase. The s orbital holds 2 electrons, the p orbital holds up to 6 electrons, the d orbitals hold up to 10 electrons, and the f orbitals can hold 14 electrons, 2 orbitals with each zone. Notice these are the maximum values that can be used at the top right of our electron configuration components. 1s2, 2p6, 3d10, 4f14, on it goes. But since each orbital can only hold 2 electrons, more orbitals must be present on the p, d, and f zones, hence why the shapes are growing with the number of electrons. Let's think about it. 1 sphere for s. That lobe holds 2 electrons. 3 lobes, or 3 orbitals for p. That's 6 electrons. 5 lobes, or 5 orbitals for d. That's 10. And last but not least, for the f orbital, there are 7 total, and that means 14 electrons potentially. Well, now we're a little more familiar with electron configuration. We know how to read the periodic table and determine the location of a specific element, differentiate between the s, p, d, and f zones, use orbital diagram boxes with spins for atoms and ions, and we've seen a shortcut where we write the electron configuration from the noble gas of the previous row instead of from the top. Then we looked at the differences between the shapes of the orbitals in each section. Thanks for sticking with me today. If you have any questions, please contact me.